All right, here we go. So it's nice. It tells us resonant circuit, right? So I know I'm going to be using those resonant equations. So on the equation sheet where it says series resonant circuits, is that still showing?
Yes, sir.
Okay, so I know that these are the formulas I'm looking for, that Fs is the resonant frequency, Qs is quality factor, EW is bandwidth, F1 and 2 are the ends of the bandwidth there. So what it wants to know is the L of this series resonant circuit. Find the value L if the resonant frequency is 1800. So this right here is Fs. And I know that that is equal to 1800. So if I set my equation, Fs, and I always recommend writing the equation before you plug in values or before you even rearrange it. And I usually like to rearrange before I plug in values. But what I'm looking for is I'm looking for L. This one may be a little bit more complicated, so I'll do it in 2 steps, right? But the first one is that if I swap the square root of LC, then it's like saying 1 over 2 pi Fs, right? And then in order to get it to just L, I would square that and then multiply it by C. So, or divide it by C. So it's like saying 1 over 2 pi Fs squared times C. If you have, you could also do this one with numsolve on a calculator. Numsolve, right, where you just leave the L blank. It's not blank, but you call it X.
Put it as an X.
Yeah, leave that as the X in numsolve, which is second sign on the calculator here. And you could leave the L as your, and type it in as X and plug in everything else, and it would also do it. It takes a little while. It's not super fast, but if you just wrote all the numbers in here and said, 1800 equals 1 over 2 pi, the square root of L, C is 2 microfarads. And if you wrote that and then said, and I would probably write on your test numsolve, just so I knew how you did it, because otherwise I don't know where the number comes from. But if you wrote that and said numsolve, that would be totally acceptable for me.
Okay.
Fs we know is 1800 squared. 2 microfarads is the C, and the L that I get is 3.91 millihenries.
Yeah, I got that doing the numsolve just
Doing
now.
numsolve? Good to go. So that would be fine. I would write numsolve just so I know how you did it. But if you didn't want to do the algebra, you want to use numsolve, that'd be fine. Calculate XL and XC. Well, XL is 2 pi FL, 2 pi 1800, because we're talking about at the resonant frequency, and L is 3.91 millihenries, and that comes out to 44.2 ohms. XC is 1 over 2 pi FC, 1 over 2 pi 1800, 2 microfarads, and XC is 44.2 ohms. And that makes sense because that's what resonant frequency means. And that's actually where that equation comes from. We're setting the F's equal to each other. Sorry, we're setting the XL and the XC equal to each other. And that's where that Fs frequency equation is coming from.
So is that saying like in all resonant circuits, the XL and XC will be equal to each other?
At the resonant frequency, they will.
Okay.
So just like your radio dial, we can adjust to 99.7 megahertz is actually what you're doing when you're doing your radio dial, right? And so at 1.8 kilohertz on this particular one, the XL and the XC are equal to each other. XL equals at XC at Fs.
That makes sense.
And that's where that equation is coming from. I'm setting 2 pi FL equal to 1 over 2 pi FC. And that's where that equation is coming from, is I'm setting it for F. Does that make sense?
Yes, sir.
So that's why it will always work out. So now it says find the magnitude at the resonance. So I'm going to use V equals IZ, I equals V over Z. The voltage on this one is 20. That's a time domain equation up here. So I'm going to multiply it by 0.707. Oops. Because that's the RMS value. Right, and then its angle says 0. And then Z, well, at resonance, the XL and the XC cancel out, and all that it is 4 ohms. But if you weren't sure of that, we could write it up here and write J 44.2 negative J 44.2, right? And so my Z total that I can see is 4 plus J 44.2 minus J 44.2, and I get 4, right? So that's where it's coming from. Go ahead.
Kind of confused on where the 0.070 came from.
That's just the RMS value. So that's like saying 20 divided by root 2.
Oh, okay.
And that's because up top, that was a time domain equation that was given. See, up here it says 20 times 10 to the negative 3 sine omega t. So that's time domain. So in order to use it with all these vectors as phasor values, I needed to divide it by root 2 or just multiply by 0.707. Does that make sense?
Okay. Yes, sir.
That's 3.54 milliamps, also at angle 0. It'll always be, because it's purely resistive once the inductor and the capacitor cancel out, so that it'll always be angle 0. Now the rest of this, I mean, you can probably see it, but if I wanted to know the power dissipated by the circuit at resonance, I could use the P equals I squared R. You could use the other ones like the S equals I squared Z. That would also be fine, but note that it's going to end up being just real power because all that we had was 4 ohms here.
Okay.
Right? So it would give you the same answer. So I 3.54 milliamps squared times 4 ohms, 50.13 microwatts. The Q of the circuit, Q is equal to X over R. You can use either one of them, 44.2 or 44.2, because they're the same. 44.2 divided by 4 is 11.05. The bandwidth, Fs over Qs, F, resonant frequency 1800, QS 11.05, and the bandwidth 162.9 hertz. So the cutoff frequencies, F1 is equal to Fs minus bandwidth divided by 2. F2 is equal to Fs plus the bandwidth divided by 2. And I'll just write those answers because that's pretty easy math. If I do the right one first. 18.5 hertz, 81.5 hertz. And the power dissipated at these frequencies, you don't need to worry about that. I mean, you could calculate them again by plugging in the Fs, but do I even want to mess with that? I don't think I do. The shortcut is that it is going to be 1 half of the P max, so I'll just say it. But I don't think we'll ask you that question on the exam.
you explain part F again? Still kind of confused on that one.
Yeah. So here's what's happening is as a function of frequency, what is the current? Right? That's what we're seeking to achieve is the maximum current. And this is a mirror image curve. And so at this frequency is the maximum I that could be achieved. Are you okay with the curve so far?
Yes, sir.
So then there's this bandwidth of where it's good, right? And by good, I'm saying that within this area, within this region, what we're saying is that just like before that 0.707, where it's still a quality, we have a quality factor of 11.05. And so notice how the bandwidth is dependent on the quality, right? So, or see the bandwidth is equal to Fs over Qs. So within this circuit, how quality is this circuit? It's 11.05, and it's just a ratio. And if it's over 10, it's considered a high quality circuit. That's why in the equation sheet, it says series resonant circuits, Q greater than 10, because it's high quality. So now this bandwidth, where it's still a quality current coming through from here on the graph to here on the graph, all of these frequencies are good, right? Because if I'm plotting it, it's best at 1800, but I'm still getting a quality signal at 1718, or I'm still getting a quality signal at 1881.5.
Okay.
Does that make sense? Think
Yeah,
on
that
your
makes
radio dial. Have you ever dialed it to, you're at 88.9 FM is what you're supposed to be at, but then you go to 88.7 and you can still kind of hear it?
Mm-hmm.
That's kind of, you're within the bandwidth maybe. Maybe it's no longer quality enough to consider it truly quality, but even here
I kind of hear it.
Exactly. That's probably the easiest analogy to think of frequencies.
Okay. And then you say I don't have to worry about the power dissipated.
No, yeah, but that's where this is coming from. The power is half of what the power maximum could be, which would be at Imax at that. But yeah, you don't have to worry about that.
Okay. That makes more sense. I was doing the only thing I have, again, back to the, I don't know why, but I keep trying to find the RMS and I do the 20 over √2 and I keep getting a different number than that.
Yeah, so 20 over √2 would give you 14.14.
Yeah.
And then we divided that because the 20 times 0.707.
Oh, then you divided that by 4.
Yeah, so that was just my V. My V was 14.14 millivolts. So now my I is 14.14 divided by that 4 ohms.
Okay. I think I was just confused. I think it was how it was written because I saw it looked like 20 times the 0.707
Yeah,
over
20
4.
times 0.707 divided by 4.
Okay.